So this is example 2 in Module 8. We have a coil of wire that's in a uniform magnetic field, and we want to calculate the torque that's exerted on this coil. So the magnitude of the torque exerted on a coil is known. Right? We have a formula for this. So the magnitude of the torque that's going to be exerted on the coil is going to be equal to the number of loops in the coil times the current that runs through a loop times the area of a single loop times the magnetic field strength times sine of the angle theta, where theta is the angle between the loop perpendicular and the magnetic field. So this coil is rotating, which means that angle is going to be a function of time. That's what makes the torque a function of time. So the loop perpendicular, I have a coil drawn here. This would be a side view of the coil. I have the magnetic field pointing to the right. The loop perpendicular is going to be the line that is perpendicular to the plane of the loop. So in this case, the angle between the loop perpendicular and the magnetic field would be 90 degrees. So this angle theta is going to be a function of time. And if we recall from Physics 1 when we talked about circular motion, basically we have a set of kinematics equations for the circular motion quantities that are analogous to linear motion. And in this case, the angle is going to be equal to the angular velocity multiplied by time plus whatever the initial angle is. So if the angle theta starts off at 0 degrees, then theta naught would be 0. But if it starts off at some other angle, we have to account for that offset. Now, if we read the problem, it says to assume that the coil rotates such that the plane of the loop starts out parallel to the magnetic field. That's actually what I have drawn here. So the plane of the loop is this plane right here. And that is parallel to the magnetic field. That means the perpendicular to the loop is perpendicular to the magnetic field. So in this case, we're going to have theta naught is equal to 90 degrees. The other thing that we need to do is calculate what the area of the loop is going to be. So we're told that this is a rectangular loop that has a length and width, L and W. So the area then is just going to be the length times the width. So if I write down the torque, this will be a function of time now. It's the number of loops, the current through a loop, the area of a loop, the magnetic field strength, sine of this angle, which is a function of time. Oops, I wrote a Q there instead of a theta. So that is the torque as a function of time. If I graph this out, it's a sine wave. Right, so sine by itself goes between plus and minus 1. Sine multiplied by some amplitude here is going to go between plus and minus that amplitude. So this is sine plus 90, this is sine of omega t plus 90, so it's actually going to start off at a peak. It's going to look like cosine. But this is what the torque as a function of time would look like. Now the reason that we want to look at this plot is so that we can make the connection or identify what the peak torque is going to be. So anytime I have a sine function, right? So if I've got some function of t, it's equal to a sine omega t plus some phase factor. This piece out here is called the amplitude, and the absolute value of that amplitude is the peak. And it's the peak because if I look at the graph here, right, this height here is going to be N I L W B, and then down here it's going to be negative N I L W B. So the peak torque will just be N I L W B, which I could identify from the torque as a function of time as being this piece here in the front. And there we are. That's example 2.